made a short video explaining what I learned about LSTMs recently, and I want to share it. So I'm creating this video. This video is for people who know what LSTM are, if you have some experience using them, and if you're curious about how its implementation is in Pytorch, if you have asked yourself the question, what the hell is hidden size and number of layers? Because if you look at the Pytorch implementation, this is the implementation, and you can see there's input size, hidden size. What do these things mean actually? And that's what I'm going to discuss in this video. So references, I really recommend Josh Starmer's explanation. It was very easy. It was one of my first videos I watched to understand, and the Pytorch documentation itself is very nice. So the main topics I'll be going through is the hidden size, the number of layers, and the output in LSTM block. What kind of output does an LSTM block give out? So this is a classical LSTM block. We have the forget gate, the input, the cell, and the output gate. And I'm not here to explain LSTM from the ground up, but basically LSTMs are blocks that basically have things such as short-term memory, which is this one, hidden state H, and long-term memory, which is hidden state C. Basically what happens, let's say you have a time series data, and let's say you have 4 data points right now, season 1, season 2, season 3, season 4, and you have 4 data points. Okay, so in one LSTM block at time t1, you can give it the first data point, and it's gonna go in, it's gonna process beep boop beep boop, and it's gonna spit out a long-term memory C and a short-term memory H, and then it's gonna go to the next time block. Time block, as in it's the same LSTM cell, but it's in the future. So basically it just loops around in a way, you could say. So then you give it the second data point, and it just processes again. It uses the data from the previous data point. So that's the long-term memory. As you can see, the long-term memory doesn't get affected as much, whereas the short-term memory gets used in every gate. And the forget gate, there's the input gate, and basically anything that's like a pattern, and you can pass it to the LSTM block. Now you have to remember, these are not 4 separate LSTM blocks, it's just one LSTM block in 4 different time spaces. So T is for time, so time unit 1, time unit 2, time unit 3, and time unit 4. It's the same block, you have to remember that. So basically these are the things, that's the formula that's going on inside Pytorch. If you look at the implementation in the documentation, the formula, it's right there. So that's the formula. If you want to understand how these formulas are working inside, I would really recommend Josh Starmer's video on LSTMs, and he explains it in a very simple and a very easy and fun way. So if you want to understand these formulas better, I suggest going to his video. Now, first thing we're going to discuss is what is happening in an LSTM. What is actually happening inside LSTM? So first things first, we'll be looking at LSTM blocks, and if we go to the implementation, and we can look at the variables, and we have the weight IH, weight HH, and bias, all these things. So I'm going to explain it in a very simple way. So if you have a look at the LSTM block, whenever an LSTM block is created, and so this is a simple LSTM, nothing much complicated. Input size 3, hidden state 1, and number of layers 1. Okay, I believe this looks like most implementations of LSTM. And what we've done here is we have created a model.png to understand the weights. So as you can see, here we have 4 different matrices, if you will. We have items.lstm.weight IH, lstm.weight HH, and LSTM biases. We can ignore that for now. So as we have seen, we have the IH and we have the HH. we have those two weights, and those weights have the dimension of 4, 3, and 4, 1, and I'll tell you why. 4, 3, the 4 is significant because 4 is for the number of gates we are using. So 1, 2, 3, 4. So we have 4 gates. As you can see, the WI, basically the same thing as this WI, the WI that's being used is 1, 2, 3, 4. It's being used in 4 equations. So that's why there are 4 weights, and 3 is it's just the input size. On the second weight H, the 4 is the same thing. The 4 is the number of the times it's being used, 1, 2, 3, 4. But the 1 is the hidden state, hidden size. So I'll be going into that right now. So basically, when you initialize an LSTM, you have these 4 matrices, sizes 4, 3, 4, 1, 4, and 4. What happens is when you give it an input, for example, 1, 2, 3, batch size 1, sequence length 2, and input dimension 3. And what the LSTM will do is it will process every sequence one by one. So what's going inside the model at time 1 is just a small matrix or vector that's 1 into 3. That's a matrix. So what happens is the weight 4 into 3 gets multiplied by the weight gets multiplied by the input, and then the bias is added, and then you have an output right here. Okay, and that is, you can see, because if you see the equation, everything is just the same thing. It's weight multiplied by x plus bias, weight multiplied by h plus bias, weight multiplied by x plus bias. It's the same thing. So you can all compress the whole equation all into the matrix multiplication. So you do this and you get the 4 into 1 matrix. And similarly, we have the WH multiplied by the HD, that is the short-term memory, and then you can get 4, 1, and then you get another matrix that's 4 into 1. This particular is basically this one. So if you look carefully, we have these connections, right? So you can say that what's happening here, this small matrix multiplication, is just what's happening from input x in these junctions. And similarly, this is just the weight multiplied by the HD being this one. So similarly, it's the weight being multiplied in these junctions. Again, if you want to get a detail of how these weights are multiplied, Josh Starmer's video, again, very good for one. And then you get the two things and you can add them together. I did not know I can do that. And basically you get a matrix, a file matrix of 4 into 1, and then that 4 into 1 gets divided into IFFT, the equation I, F, the gate G, and the gate O for further processing. Now this is just for hidden state 1. Okay, this is what I'm showing you on hidden state 1. I will now show you what a hidden state 2 of an LSTM block looks like. This is what it looks like when you have LSTM hidden state 2. And we have increased the sequence length to 4. So first things first, we have 4, 3, and we have 8, 3. It became 8, 3 because the number of hidden state is 2. The real formula for WI, if we have here, is 4 into hidden size, and the hidden size we chose here was 2. So 4 into 2, 8, and 3 we have the input dimension, and again 8 into 2, 2 is the hidden state. If we look here, WHI hidden size, 4 into hidden size, hidden size. So that gives us why the size of the matrix is like this. So basically, as you can see, the more you increase the hidden state, the larger the matrix inside the LSTM becomes, and basically larger matrices can be translated into more information or more complex patterns being recognizable. the model being more capable of learning more things. So basically it's the same thing. The A3 matrix, weight matrix gets multiplied by the input, and you get the 8-1 matrix, and then tensor. I should use the word tensor. You get the 8-1 tensor, and the 8-2 and 2-1 tensor gets multiplied, and you add them together, and you get the equations I, F, G, O, and then you pass them through their little functions, the sigmoids and the tan H's, same as the formula. And then you can process them further into CT and HT, just like in the equation CT, HT. See how the matrix multiplications are the standard matrix multiplication, H2 2-1 equals to H1, but these are different. These are 2-1 2-1 equals to 2-1. These are Hadamard product. So knowing these different kind of matrix multiplication is important because it can mess with your calculations. So basically what happens is all of this input gets processed, and then it sends off the CT and the HT to the next block, time 2. I'm saying next block, but I want to make sure whenever you're initializing an LSTM block, it's just one LSTM block. This just means I have one LSTM block. These are not multiple blocks. I have to emphasize that because I was confused about that thing for a very long time. Because whenever I was working with LSTMs, I used to get confused. What is input size? Does it mean the length of sequence that I can give it? What is hidden size? What is number of layers? So it was very confusing for me. But I'm here, so if you have been through the same thing, I'm here to explain. You can do the same experiment. If we have the hidden state 2, right now I think, hidden state 2. If we increase the hidden state, if we use this, we have a new model.png. 4-3 becomes 8-3. As you can see, the weight, the size of the matrix that's inside the LSTM has increased. So, summary. The hidden state is just the internal dimension. As you increase the hidden state, the size of the internal equations increase. So when the hidden state was just 1, the matrix that was going into these equations was just 1 by 1. Okay, but when you go into hidden state 2, the size of the matrix that go into these equations become 2 into 1. Okay, so basically you're increasing the dimensionality of the equations that's happening inside the operation. So basically, if you give it a 3-dimensional input, basically let's say you are giving it 3 different quantities from a sensor at time t. So you have a time t, and from that time t you're giving it 3 different readings. Okay, then you can all of them get processed at the same time inside the LSTM block. Okay, if that makes it more clear. If you have any confusion, you can ask me in the comments. I will be happy to. Number of layers in LSTM blocks. Now, the number of layers parameter, the number of layers, as you can see here. Okay, the number of layers basically means how many LSTM you stack one after the another. Now I'll explain this like this. So let's say you have an LSTM. What will happen is you have the inputs, input xt1, xt2, xt3, xt4, and when you pass them on, when this LSTM block finishes processing the data at time t1, it passes it on to the next block. And then once this finishes processing the data, it passes it on to the next block. And that's how it goes. So that's what the number of layers mean. So we have this example where our number of layers is 3, and pay close attention to the model.png. Ta-da! So now instead of 1 LSTM block, you have 3 LSTM blocks. You understand? And all of them are stacked one after the another. You have 3 LSTM blocks, cells, that you're using. And this is the simplest depiction I can show you for easier understanding. But when you give it the data and the data is flowing through the whole system, this is how it should look like. Now, this is what layer one layer of LSTM looks like. It's just one LSTM block. It's just one LSTM block. And the data just flows, data point 1, data point 2, data point 3, data point 4. And it processes it, and it gives you out the long-term memory and the short-term memory. So I hope that clears out what layers mean. Layers just increase the number of LSTM blocks that you're using, and it can be very beneficial for complex pattern recognition. So if your model is not performing very well, you might want to increase the number of layers and just test it out, how it goes. Output of the LSTM block. The output of an LSTM block. Okay. Now, this is the same simple implementation of the LSTM code, but what the difference is, now I have printed the output shapes, the output tensor itself, and the output tensor HT and CT. Whenever you give LSTM an input X, it gives out two different things. The output matrix, the output tensor, and the two separate tensors, HT and CT. Okay, so we're going to execute this real quick. And voila. What we have here is the input shape 143. As you can see, the input shape 143 right here. Layer 1. So after the layer 1, it gives out the output shape of the LSTM, the output shape of the LSTM block. Okay, 143. It's the same as the input. Okay, and HT's dimension is 113, and CT's dimension is 113, and CT's dimension is 113. Let's see what's going on. And the output tensor, you can look at the output tensor. It's a 143 tensor, and the HT tensor. Now if you look carefully, you can see the last list of the output tensor is the same as the HT, the short-term memory, minus 0.1909, minus 0.1909, 0.2598, 0.2598, minus 0.3414, minus 0.3414. Now I'll tell you why that's the case. So let's say the input is 4 into 3. That means sequence length of 4 and the input dimension is 3. Now the input gets divided into 4 smaller tensors for different time span. Okay, T1, T2, T3, T4, and they each get pushed into the LSTM block. So the first LSTM block, processes the data, and then it spits out C1 and H1, short-term memory 1 and long-term memory 1. And after the output, it gets saved. Okay, after that, the second tensor gets into the LSTM block at time T2, and it processes it and again saves it. The output gets saved. Now the output, the short-term memory, what we're saving is the short-term memory, and not only are we saving the short-term memory, we are also passing it on to the next LSTM block. So again, the third data point gets processed, and the fourth data point gets processed, and all of this gets collected, and then it gets merged, and we have 4 into 3 tensor, same as the input. Okay, and we also get the long-term memory matrix and the short-term memory matrix. So this is essentially what we get out of the LSTM block. It's very simple. Basically, if you look at the documentation, it's written in a very simple language, I believe. Output, HN and CN. You get 3 different things. The output, which is basically concatenating the output from features HT from last layer of LSTM for each T. Last layer basically means if it was a stacked system. So the last layer, they mean. But anyway, so basically what we are getting is just the HT from each layer together. So we can choose to use the entire thing into our next layer, or we can just use the last layer. So in my implementation and in a lot of implementation, people only use -1. -1 basically, if you look at the the data set, the output tensor 143. So 4 is the sequence length, and -1 means it's going to take the last sequence. And so after this operation, layer 1.5 ouch dot shape, layer 1.5, it becomes 1.3. So basically, the tensor that was once 143 becomes 1.3. You know, you take out the last, you essentially choose to use only the last tensor. Okay, and remember, this and this are the same. So that's what you get for the output of the LSTM, and then you can, you know, pass it on to a linear layer, and then you can process it, and you can train it, and you can train it, and you can train the model to do classification, regression, whatever you like. LSTMs are very powerful models, you know. They were very revolutionary and very widely used and very well liked. But I believe it's one of the models which is a little harder to understand, because if you look at neural networks, it's very easy. Neural networks is just a bunch of dots and just matrix multiplication. Whereas in this one, if you do not understand how it's working internally, you might be confused on what's going on. That's all from me, and bye.